Good evening, all. Welcome to week 9 of the session, live sessions for Optimizations and Fundamentals course. To those of you who are joining for the first time, the aim of these sessions is to help you solve your assignment problems, and if you have any queries, we can discuss them in any of the subsequent or any of the assignment problems that we have discussed before, or any of the concepts during this particular week lectures. Maybe we'll wait for a couple of more minutes for a few more people to join, and then we'll get started. Think we'll get started. So this week the session focuses on the following four topics. So we'll discuss first again briefly review what we discussed in the last week on constraint qualification. This time we'll give a few other conditions as well. Last week we discussed only the linear independent condition. Now we will have two more constraint qualifications, and from there we'll discuss what is called Slater condition. And subsequently we will see what Lagrange and how is it related to the dual function. How are these two compared with each other? And finally, we will see some of the statements that I would prefer if you would actually go through the lecture videos to see through the entire derivation of the strong duality. But here I'll just present you with the statements that basically the conclusions from whatever the video from the lecture video on how the strong duality is established in case of convex optimization. So the first one is the concept of constraint qualification. So last week when we discussed, we have a set S defined as all the set of points X that satisfy the condition J of X less than or equal to 0. These are my set of inequality constraints. Yeah, you can also have the equality constraints as well. Let's restrict ourselves to inequality constraints. The G is a function mapping from R into R, and it is continuous and differentiable. S is a subset of Rn because it only includes the values of X for which G of X is less than or equal to 0. And we define A as a set of X star which satisfies these conditions exactly. So this is called an active constraint. These are called active. What this means is these are the points that are lying on the boundary of my constraint function Gi. So all the points lying on the boundary will form a set called the active set. We say a constraint qualification holds if this we defined last week. We defined something called a tangent cone. The tangent cone should be described as if you recollect, tangent cone is essentially defined as the set of vectors D such that D equals xk minus x star by tau k, where the set xk is k tends to infinite and you have tau k going to 0. And all these points xk should belong to the interior of the domain. This will form the tangent cone. But then the problem that we told you that we discussed last week is this set S cannot be always be described in terms of points. So the set if this set if described in terms of inequality constraints like this particular constraint over here, then we assume that each and new like the so when you decompose this test into sorry hi good evening. So this constraint we discussed in the last week, where the tangent cone is described by the vector d such that grad g transpose d is less than or equal to 0 for all the active constraints. So whenever we have an active constraint, if this particular condition is satisfied, so which means if you have gi of x something like this, and this is a point line, this is my gi. and this is a point that is lying on the boundary, then this particular constraint will be an active constraint, so Gi will belong to A. Now what is the condition? This condition says that D is a direction, D will always point towards inside the domain or something like this, and grad G will be the normal to this one. Like our constraint is Gi is less than or equal to 0, which means if I move along this direction, the Gi value will keep on increasing, and then this is the direction of D. So if I take a dot product of D can be any of these vectors. So it will make an obtuse angle with respect to the gradient normal. So this particular dot product will be less than or equal to 0. So that is all the set of vectors that satisfy this particular constraint will form a tangent cone. That is what we defined it last week. And then we also told that this alone is not sufficient, because you can have several constraints, like this G you can have for all the constraints Gi. You can have 1, 2, 3 up to m constraints or whatever, depending on the number of constraints you have. All the constraints may not always be required. So how do we say that these tangent cones are not defined in some redundant ways? Like there should be only one way to uniquely define this tangent cone, and the condition that is used is we told that this grad Gi should be linearly independent. Like whatever vector that we are using here, the gradient normal, whatever we are having here, should be linearly independent. So for example, if you have two constraints, say this is one constraint boundary, say this is G1, I can have another constraint boundary, something like this. So when I say Gi less than or equal to 0, it is all this region. This is G1 less than or equal to 0. And similarly, I can have another constraint, that is G2. Say this is my G2. G2 less than or equal to 0 could be this region. So this intersection region, whatever is in this one. So if this is the point, if this is an I'm saying both G1 and G2 are active constraints, which means X should lie at the intersection of these 2 points. So this is my X star. So at this particular X star is what we are trying to find. So at this particular X star, when I take the normal for G1, this is my G1, so this will be normal to G1. So this is grad G1 at X star, and this is my G2, so this will be something like grad G2. So if you can see, if this is grad G1, then how do I get the tangent? I have to select all the vectors that are making obtuse angle with respect to this particular normal. So all those things which make obtuse angle are all the vectors that form like this. All these vectors will make obtuse angle with respect to grad G1. And similarly, I have to take all the vectors that make obtuse angle with grad G2 as well. So that will be all these vectors. And now I have to take intersection of all these sets. It's like it should be satisfied for all the ones. So the only vectors that will satisfy both the constraints are these ones, whatever is inside. These vectors. Maybe I should have used different color. Yeah, these vectors. Only these vectors will satisfy that particular constraint, and they are the ones that we are calling that will form the set of this tangent cone. So, but for this, what is the main criteria that we require is, again, now this intersection region is formed by both G1 and G2, intersection of both G1 and G2, which means both G1 and G2 are required to define these particular vectors. If I have only G1, then it would be all these vectors. If I have only G2, then it would be all these vectors. Only when I take both of them together is when I have the feasible region, and these are the vectors that are uniquely defined. And this kind of thing is possible only if grad G1 and grad G2 are linearly independent. Now you can think of a different scenario where let's say you have, say this is my G1, and say this is my G2. You have something like this, and let's say this is my point X star. Let's say G2 is tangent to G1 at this particular X star. So if I construct a normal, then grad G1 will be parallel to grad G2. Both the normals will be parallel to each other. So the tangent cones, if I construct for grad G1 or grad G2, anyone, I can use only one of them, and I will be able to construct the entire tangent cone, right? So it will be all these vectors. And in order to construct any of these tangent cone, I'll require only one of this function. Either G1 or G2 is sufficient. I actually don't need both of them to do this. So this is essentially because these both are parallel to each other, which means they are linearly dependent. So the moment you have linearly dependent things, then the way you define tangent cones, like one of them is sufficient, other one will be redundant. So So explicitly we are stating that is if you have linearly independent gradients, then those are the G's that you should be using to describe your domain S. That is the first kind of constraint qualification we discussed in the last week. There are two other kinds of constraint qualification that we'll be discussing this week. This is the CQ1. Okay, let's put some name. This is CQ1 and this is CQ2. This is just another way to say, yeah, yeah. No, it's a cone is because it is a set of vectors, right? So the way we define cone is a set of vectors such that it has origin, and if you scale it, the scale vectors also belong to the same set. So it is called a cone. I mean, that is how a cone is defined. Yeah. So coming to CQ1, so in addition to linear independent is one way of saying it. The other way of saying it is, let's say you have the same problem where x star belongs to S and in a vector D exists in Rn such that for only the active set, you have one of these to be satisfied. Either grad G times D is less than 0 or is equal to 0 and G is affine. By affine, we mean that the linear combination of them should also be in the same line. So affine is essentially linear. So if Gi is just linear, no nonlinear equations or anything, Gi is linear, then the constraint qualification holds. So how do we explain this statement is also in the same way as before. So previously we just told that it has to be less than or equal to 0 and everything has to be linearly independent. If all these constraints are linearly independent, so let's take another example. So when I say G is an F1, it means it's just a set of linear constraints. When you have a set of linear constraints, something like this, then normals will always be, the normal for this will be something like this, the normal for this will be something like this. And when you extend them, this will be the tangent cone that will be formed. So when you have a set of linear constraints that Gi is affine, then you will always have the scenario that you can always have these normals that are linearly independent. Like it is indirectly saying the same thing. So if they are linear, if GIs are linear, then it is assured that you will have linear independence. So it will anyway satisfy the same constraint qualification that we have as before. And the other constraint is slightly different one. So instead of focusing on the gradient, here we will be saying with respect to the actual function value itself. So there are two variants of it. So either you have G of x at less than 0 and that function is convex. So if your inequality constraint is a convex function, then you need to have for every x star, you need to be able to find a hex hat such that the value of G is less than 0, because you can also think of this in a simple way. The derivation, like if you take this particular statement, what does this statement mean? I can take this as grad Gi transpose D less than 0. Grad Gi is basically Gi of some x hat minus Gi of x star by x hat minus x star, and D I can take it as x hat minus x star. Oh, I'm just removing tau k for now. So what we are saying is this should be less than 0 from this particular statement. So if I just remove these things, x hat not equal to x2, so we have that statement directly coming here. So Gi of x hat, but I told you that x star is I belongs to active set, so Gi of x star should be equal to 0. So this should be less than 0. So essentially this statement is equivalent to this statement. So where is the convexity coming here? Why do I need it to be convex? You can do the same thing here as well. Convex affine, whatever it is. So where is the convexity coming? So if, for example, if I say it in a slightly different way, let's say if you remember last week when we discussed on convexity. So if you have a function g that is, if g is convex, then I can say that g of x plus something like 1 minus alpha delta x maybe let me put it on, let's take it like this, g of x plus 1 minus alpha into delta x. This can be written as, or okay, we'll put it as something like this, g of alpha into x plus 1 minus alpha into x plus delta x will be less than or equal to This is something you already know from convexity definition, and we can rearrange this as the alpha x and alpha x gets cancelled, so this will be x plus 1 minus alpha times delta x. If you apply the Taylor series expansion for this, this will be g of x plus 1 minus alpha grad g delta x plus some higher order terms. So this, whatever the higher order terms, will always be less than or equal to, can I write it like this? I'm just removing the 1 minus alpha. Alpha is between 0 to 1, so 1 minus alpha will also be between 0 to 1. So if I remove that one, then I can write it in this way. So this entire thing will be less than or equal to this particular quantity. I think we agree till here. So what we are trying to do now is, for every x star, we are trying to find a new point x hat. So this is my x hat. So g of x hat will be less than or equal to g of x star plus some quantities that will keep going, some higher order terms that we have. So if g of x star equal to 0, this particular quantity equal to 0, and this particular grad g is times whatever d that we are defining is less than 0, then this particular quantity will also be less than 0 always. That will always be true because it is a convex function. This thing is true because we are using a convex function. If it is a concave function, then yeah, understood. Yeah. So this is the next definition. Instead of convexity, you can always have the affine definition. So why is strict less than coming? When you have a convex function versus an affine function, the difference comes in your second order derivative. So for example, I have a del square g here times delta x square by 2 factorial or something. So whenever I say it is an affine function, then whenever we say convex function, then this particular thing is assumed to be positive semi-definite, or you can assume this Hessian. This is basically the Hessian. This should be greater than 0. If it is strictly positive, then you have this equality cannot be true. But the moment you say it is an affine, then G is linear. Affine is basically implies G is linear. If G is linear, then del square G will be 0. Then this term will just go off. If that particular term goes off, then and this particular term is 0, then G of x hat will be less than grad G times delta x. And we know that grad G times delta x, grad G is this and delta x is my d, and that is less than 0. So the strict inequality will come if it is a convex. If it is an affine, then the other terms can be there that can make this equal to 0. But if we forget about the math, the only thing that we are trying to do is the way we are trying to get this d should be in some way that will help me to define my tangent cone uniquely. Like I don't need any redundant values in the definition of GI. If there are 2 or more GIs which are giving me the same information about DI, then I should eliminate one of them. That's the whole idea here in this constraint clarification. This is clear. The next one. Yeah. So the next one is the concept of Lagrangian and dual functions. So this is our standard optimization problem. We have to minimize some function f of x subject to the constraint gi less than equal to 0 and hj equal to 0. The Lagrangian, which we already discussed before, is f of x plus summation of lambda times gi plus this particular function. This function can also be treated as when we try to minimize this L over all the x possible. So here, if you see the difference, this x belongs to Rn and not x belongs to S. So like in this problem here, x should belongs to S, where S is defined by this particular combination. But when the moment we convert it into the Lagrangian formulation, we are doing it, we are solving the problem as an unconstrained optimization. Yeah. Okay. So let's say at a given x value, I fix the x value, x is not changing. At a given x, let's just take one problem, a simple case where you have something like for a given x value. So since x is fixed, I'm putting x hat. Lambda and theta is something. Let's say theta is not there. Understanding with one would be sufficient. This will be something like f of x plus lambda times g of x hat. So x hat is some fixed value. So if I plot this as a function of say lambda, this is my L of x hat comma lambda. So what will this function look like? F of x is my intercept, so it will be some function, something like this. This is my intercept, and the slope is my constraint. So what we are trying to vary is this particular lambda. So we are just trying to keep changing it till this is for a particular x hat. Now if I change x hat, I will have a different line. So if I change x hat, then maybe this f of x hat will change. So it will come somewhere here, and g of x hat is basically the slope. That will also keep changing. So you'll have something else. So let's say this is for some x1. So similarly, I can have something else. This is for x2. I can have something else, x3. So if you keep changing the values of x, your line here in this is basically my dual space. So the line in this dual space will keep changing as I change the x values. So what we are trying to do is we will keep changing x for all the entire as an unconstrained problem, and then we will find the minimum value of this L. What is this L? The minimum value of this L will happen when, if for example, we are restricting to the case where lambda greater than or equal to 0, that is another restriction we are keeping here. I think I would have written here. Yeah. So lambda greater than or equal to 0. So we're only focused in this particular side of the quadrant. So for all the scenarios, what we wanted to try is minimize this particular value. So it can be here. If for a particular case you go to negative, then it will keep going in negative, and then you will eventually reach minus infinity, which we are not considering, because we are based on the assumption that we have a finite optimal value. So the worst case it can go is up to 0. Otherwise, you need to find this particular intercept. This will be the minimum value that this particular L of x hat comma lambda will reach to. So this is what we are trying to do here. We are trying to vary different x. As you vary the x, this line will keep changing. So it will keep moving across the y-axis, and the slope will also change. The slope and intercept will keep changing. So at particular value of x, you will have the minimum intercept. So every line above or below that particular value of x will fall at this particular one, and this intercept is what we are trying to find. And that intercept is my d of lambda comma theta. And then what we try to do is we try to maximize this particular intercept value by varying my particular lambda and theta. So this is essentially linear function, because this is essentially some a plus lambda times b, right? This is basically like ax plus b form. If I write it like b plus lambda times a lambda. This is something like ax plus b, where x is replaced with lambda. So this is a linear function, and it is concave. So okay, first, is it clear up until here what we are doing in the dual space? If I put h of x, then theta will also come into picture. Then it will be difficult to draw, because then it will be like a three-dimensional one. So I will have lambda, I will have theta, and then both of this will give me some. This is my L of x hat comma lambda comma theta. So how will it look is something like in the three dimension, it will be some hyperplane. It will be difficult to draw just today. Let's say if I draw contours, you can think of this like for one value. So it will be f of x hat plus lambda times g of x hat plus theta times h of x hat. So this particular thing is some ax plus by plus c equal to 0, right? Is equal to some constant. So whatever value you get here is L. So this is essentially a plane equation. This is my say x, this is my y, this is my intercept. So it's like ax plus by equal to some constant. So you'll have some contour here. For every x hat value, that contour will keep changing. So the contour will be some line here. It will be something like this. For a different x hat, you will get a different line. Maybe something like this. As you keep changing, the values will keep changing, and eventually again the bottom line is the same. All you're trying to do is find these intercepts. What is this intercept and what is this intercept? Okay. So the next point here is we are saying that D is a concave function. So how do we say that? So what is my D? D is essentially something like f of x plus, let's just take one value, g of x, h of x. And we are trying to minimize this over all possible x so that x will be eliminated from this. So just put infimum of x. So once I try to minimize this, then x will be eliminated and all that will be remaining, the variables will be lambda and theta, and that is what my d of lambda theta is. So yeah, you can always check for convexity directly. So all we can do is just put d of alpha lambda 1 plus 1 minus alpha lambda 2. Let's just take lambda for once because it's the same for both of these things. I'm just taking lambda here and I'm just assuming that theta is not there, h of x is not there. So this will be what? So you'll have f of x plus alpha lambda 1 plus 1 minus alpha lambda 2 times g of x. This will essentially give me infimum over f. X, you just take the terms for lambda 1. So if I take alpha times f of x plus lambda 1 g of x and 1 minus alpha times f of x plus lambda 2 g of x. What would this term mean? So what we are trying to do here is, let's say this is some function, infimum of x, alpha times, let's call this entire thing capital F1 plus 1 minus alpha times capital F2, and F1 and F2 both are functions of x. Maybe I should have written. So what can I say about this? Will it be, say, let's say I want to comment on something like this, or I don't even have to write alpha 1 and alpha 2. Let's say alpha 1 and alpha 2 are absorbed into these functions. So it is basically sum of two functions. Whatever I have on the top can be written as f of f1 of x plus f2 of x. And all I'm trying to do is find the minimum of this. So what can I say about the minimum? So what will it be in relation to, say, something like infimum of f1 plus infimum of f2. So what will come in between? Should I put greater than, less than, equal to? What will come in between? So essentially I'm trying to do minimization of two function values, sum of two functions, versus take only one function, find the minimum, take the other function, find the minimum, and then add the two minimums. So what will be the relation between this quantity and this quantity? If you want to visualize, you can think of this as, let's say this is f1, and let's say I have another function. This is my f2, and when I do f1 plus f2, so it will be something higher than both f1 and f2, keeps reducing, and then it will go something like this. This is my f1 plus f2, right? So the minimum of f1 plus f2 will be greater than the minimum of either both of them individually, right? In some scenarios, they can be equal to each other. If they exactly match, then they can be equal to each other. But in general, what can we say about this is, I can put something like this. In general, the summation, the minimum value of the summation of two functions will be greater than or equal to the minimum summation of individual minimum values, right? And what is this individual summations? This is essentially my d of alpha times d of lambda 1, and the other one is 1 minus alpha times d of lambda 2. And this is essentially means d is convex. This particular relation is true. Sorry, d is concave. If it is less than or equal to, then it is convex. If it is greater than, it is a concave. Is this clear? Yeah. Okay. So that is the next point of it. And when we try to minimize a convex, so when we try to maximize a concave function, you can always multiply with a minus sign and it will become a minimum. And that minimum will be a convex, like the negative of a concave will be a convex function. So maximizing this particular thing is equal to minimizing the negative of it. So this is essentially a convex optimization problem. So which we know that once we know it is a convex problem, then we know that global minimum, all the things that we discussed last week will apply. So the next thing that we are saying here is we define d of lambda to be the minimum value of this Lagrange, and the maximum value of this particular d will always be less than or equal to f of x star. So what do we have to say from here is, if you see this equation, we know g of x is less than or equal to 0, and we know that lambda is positive. So this is some positive quantity multiplied with some negative quantity. So this will be something that is negative. So if f of x star is the minimum value that is possible, and then you are removing something from that. So this L will always be less than f of x star, the optimal value. And this L is my D, so D will always be less than or equal to f of x star. So this is like your weak duality. This is basically my optimal value of primal, and this is my optimal value of dual. This is a short thing that haven't been used, but this is another way to create a dual. So you have a function f of x, and you want to make the dual of it. So this is another way of defining the dual. So you take a function f star of y as the supremum of this y transpose x minus f of x. So if you want to understand this clearly, so what we are trying to do is, let's say this as some quantity b equals to maximum of supremum of y transpose x minus f of x. So if I'm saying b is the maximum value of this, what does that mean? It means y transpose x minus f of x will always be less than or equal to b. To put it in another way, it means f of x is greater than or equal to y transpose x minus b. If you want to see it graphically, let's say I have some function. So this is my f of x. So what we are saying is this is x, and this is my f of x. Y axis is my f of x. So what will be y transpose x minus b? So minus b is the intercept, and y will be the slope. So it will be some line, something like this. This will be my minus b, and the slope of this line is my y. So when I'm saying f star of y, it essentially means as I keep so for all the values of x, what is the value of y that will essentially make that will give me the maximum value of this particular b, and this particular b is the intercept. So minus b it intercept. So instead of saying the maximum, it essentially means all you're trying to do is find this intercept such that so you'll keep this line, you'll change this line to something like this. You can change this line to something like this. You keep changing the line, and then you'll try to find that particular line which will satisfy this particular equation such that the entire f of x, the entire curve will lie above this particular line. So whatever line I have chosen, the f of x, the entire f of x, this particular region should lie above that line. So all these lines, this particular line will be invalid, this particular line is okay, and this particular line is okay. Out of these two lines, again we will solve the problem in a different way. So once we find f star of y will essentially give me all these lines, and out of all these lines we'll again try to maximize this particular value, maximize this particular intercept value. So like the original problem, if the original problem is to minimize f of x, then what we try to do in the dual space is we try to maximize this intercept by varying this particular y. Both will eventually be the same. If you're trying to minimize this function f of x, or you try to find a line such that this intercept will be maximized, so eventually it will go something like this, and this particular, or this might be the value at which that will be minimum, and that is where the optimal value of fx will be reached. This is just another way to define a dual in addition to Lagrange. Under f of x curve, okay, that's line you are saying. Dual space is essentially what, when I say dual space, what I mean is here there is only one variable y, right? Y is my dual variable. So these lines, whatever I'm drawing, they are in the dual space. This is whatever this line, y transpose x minus b. So I have used the same domain. I have used the same axis as both primal and dual space in this particular case. So if I am referring to y, if I am referring to x and y, then it is a dual space. If I am referring to f and x, it is a primal space. So your x is one variable. The other variable is with respect to y. So when I say f star of y, so this y axis can be with respect to if I want to draw it in a dual space, this is my x, this is my y. With respect to y, if the x-axis is the variable y that I am using here, and then I am trying to represent this function, then it will be in the dual space. Currently, this particular thing, whatever I have drawn here, is f of x plus x. So this is in the primal space. In the primal space, I am trying to draw this dual variable as different contour lines. So if I take all these contour values and find these intercepts, and these intercepts will come here. So for example, let's say for this particular line, if you take this particular line with value say y1, and I got a slope b1 or something, then that particular value, this is y1, then f of y1 will be some b1. So this will be one corresponding point for this particular line in the dual space. This will be one point. Again, I can take a different line. So let's say this line is y2, and this particular one, let's say, is b2 or something. Then I'll have another point b2 here, and I'll have a different y2 here. Then this will be another point. So if I do all those points and then plot, then that this will be in the dual space. Here I have taken f of x and x, so this is primal space. In the primal space, I'm just drawing this one. Okay. The next one is with respect to convex optimization. So here we just take the convex function. So f of x, g of x, and all these are convex functions. But then we define a set G such that f of x is less than or equal to t. Like we have u v t such that f of x is less than or equal to t, g of x is less than or equal to u, and h of x less than h of x equal to vj for all your number of whatever constraints you have. Then the primal problem is essentially what we are trying to do in the primal problem is we are trying to minimize t. If this is minimized, then this will also be minimized, and then this is equal to 0 in our primal problem, and this is also equal to 0. So u and v will become 0, and you have to find a t that will minimize this. So my objective function is t. I'm trying to minimize t. So if this is minimized, then anything less than it will also be minimized. So f of x will be minimized. This is my primal problem. So if I want to convert it into dual problem, we just have to take the Lagrange of it. So the Lagrange will be something like this. So u will be lambda times u is lambda times g of x, and theta times h of x plus f of x is basically my t. So if I try to minimize this, then I'm trying to minimize my Lagrange function. So these are equivalent. So this will be my dual problem. This will be my primal problem. The only advantage that we get here is if you see in the dual space is basically even in the primal space, this is a linear problem. Like, yeah, we know f of x, it can be some nonlinear function. It can be any function, whatever it is. But then the way we defined it, if we define g in this particular way, it becomes a linear function. So this is basically just t. So you can think of this as c transpose x, where your c is 0, 0, 1. Transpose your x is basically u v t. So this is a linear problem. C transpose x such that these things are satisfied. And again, even in the dual space, it will be a linear problem. And we know how to convert from primal to dual in linear space. Like if you have minimize C transpose x such that ax minus b equal to 0 and x greater than equal to 0, you can just convert it into dual space. You just convert it into maximize problem. We are not doing that anyway here, but you can also use the Lagrange form of it. You can see the derivation. If you have gone through the lecture video, you can see how this particular logic can actually be used to derive this particular transformation. You first convert this into the Lagrange, get the Lagrange from this in terms of x, lambda, and theta, and use that Lagrange to put in your, from this you put t of lambda theta, and use from there you can directly get this dual form. So the concept next that is important here is this particular thing is a linear equation. This is my something like my x, and this is something like my slope. So this is something like y transpose x. So this is basically some linear equation. So this is the linear equation, and we are saying this particular point lies on G. So if somehow I can plot this particular function G, then this particular dual problem is essentially a hyperplane. And we are saying it is supporting hyperplane because it is passing through particular G. So if you try to visualize this, let's say one of them is T and one other one is U. For now, let's say V is not there. Let's say the equality constraints are not there. If they are also present, then it will be some 3D problem. But to visualize, let's even 2D will be sufficient. Let's say we have only inequality constraints and we have an objective problem. We have an objective function. All of these are convex. So if let's say f of x is less than or equal to t, this particular g, whatever I can draw, is something like this. It could be all the points here. This is my set g. This is the boundary of g. So what we are trying to do again is, if I want to put the dual also in the same space, so lambda theta will be the slopes. So since h of j, hj is not there, theta will be 0. So the only parameter is my lambda. So how will it look? It will be some line, but that line should have a point on this particular space on the G. So we are saying UVT should belong to G, and from there you draw a line. Maybe I should have taken a different point. Let's take this point. So a line something like this. The slope of this line will be, so what is the equation of that line? It will be lambda times lambda transpose U plus T. This is my line. X-axis is this. So this is something like mx plus T. So C is my teeth. So this is my intercept. And the slope of this will be lambda. So what we are trying to do in the dual problem is we are trying to change the variable lambda. So we are trying to change the slope of this line such that this intercept is maximized. So eventually you will find a point such that this intercept will go and touch this point. And that's when and what is this point? This point is basically the minimum of with respect to the primal problem. In the primal problem, we are trying to minimize this t, and this is the minimum value of t that you can get in this particular case. And in the dual, we are trying to again move this line so and so this point will keep rising. So from primal it will keep falling down, and from dual it will keep increasing. Eventually they'll meet at the same point. That is what the strong duality tells you. So from strong duality, all we will be saying is this the maximum intercept that you can get will be equal to the minimum value of t that you can reach in this particular G. That is the duality, strong duality in case of convex problems. To put it simply, you have the primal optimal should be equal to dual optimal, and you can get that by maximizing the maximizing this particular intercept, maximizing the intercept by varying the slope of that particular line. Is this clear? Are there any questions or okay? I think there are no questions. I guess there are no questions. Okay, then we'll quickly move on to the problems. These are some simple problems. It might not take that long time, but you can just quickly go through them. So you have the normal optimization problem that we were discussing previously. So f and g are differentiable functions, and the set S is defined as a feasible domain. Now at a particular point x star, if you have g of x star equal to 0, and there exists a direction d for which grad g transpose d is greater than 0, for some d belongs to this tangent cone, does constraint qualification hold at x star? I mean, is it true or false? Will the constraint qualification hold or not? How do we define that? We define tangent cone something like the set of vectors d such that you need to have this to be less than or equal to 0 for all active constraints, right? We are saying g of x star equal to 0, so this is an active constraint. And we are saying there exists a which is greater than 0, which should not be true, right? But however, if we are saying, so why did we start with this entire tangent cone idea, is essentially we can use this to filter out some of the points from our original case. So if this particular thing is with respect to f of x, then it would have been different. But with respect to the constraints, this particular gradient times d should be less than or equal to 0. That is how we defined it to be. So constraint qualification will not hold that particular x star. Is this clear? Okay, so it is clear. Okay, we'll move on to the next problem. So we have CQ1. If you recollect CQ1, that is with respect, again, I have anyway written it over here. It holds that x star is for a collection of constraints gi. If there exists a d belongs to Rn such that for each active constraint, we have either this to be strictly less than 0 or it is equal to 0 and gi is affine. So you either need to have this or you need to have this plus this. Then you say constraint qualification will hold, the CQ1 will hold at that particular point x star. So let's say this is my objective function f of x and this is my g1 of x, g of x. And this is my particular point x star, 2 comma minus 1. So with this information, can you tell me whether the constraint qualification holds at this particular point? How do I solve this? So there are two conditions that I need to check. So let's, for both of these conditions, anyway, I would start out with finding what is grad g. So let's first start with that. What is grad g of x star? Basically 2 comma 4. So this is my grad g. And now I need to find a d. So like there are two possibilities. So let's do one by one. So if you take the first one, so that is grad g times d less than 0. This implies you need to calculate 2 4 times some d1 d2 is my vector should be less than 0. And the other condition says grad g times d equal to 0. If you do this, then it should be 2 4. Maybe I'll put some other values here, d3 d4 equal to 0. And I also have to check whether g is affine. By affine we mean it is a linear. This particular function is linear, so this is true. And can I find d3 d4 such that this is equal to 0? I can choose, say, d3 equals to 1 and d4 equal to minus half. I can choose this particular combination and can then make this equal to 0. So this is being held satisfied. If either one of them is satisfied, then I can say CQ holds, but you can also check the other one. Can I choose any d1 into, I can easily choose d1 equal to say minus 1 and d2 equal to minus 1. And this particular quantity will be less than 0. So this is also satisfied. So if one of them is satisfied, then the constraint qualification holds at that particular point. This is true. Is this clear? think this is clear. Okay, we'll move on to the next problem. Okay, I have some objective function with some constraints. So does this have a slider point? I think I missed out the slider point during previous one. So uh, when we have this particular constraint satisfied, the second one where you have GA of x hat for some x star which is satisfying the active constraints, then you have another point x hat that is called the Slater point if it satisfies these two conditions. If GI is convex, then GA of x hat should be less than 0. This should be at least one point should exist like that. And if G is affine, then it should be less than or equal to 0. These constraints are satisfied, and that particular point is called a Slater point. So for this function, do I have Slater points? So this is my f. This is my g1 of x, and this is my g2 of x. So how do I check for Slater condition? So first question, so is this convex? We have two possibilities. We have to check whether convex and affine. This is a convex function, x1 square plus x2 square less than or equal to 9. So if you just plot it, so have, let's say this is my x1, this is my x2, and this is the first one. Let me just draw the final one. So x1 square plus x2 square less than or equal to 9 will be a circle with radius 3, and x1 plus x2 less than or equal to 1 will be a line, something like this. This is my g1, and both the constraints have to be satisfied. So it will be something like this. This is my fifth region. And what does Slater condition say? So if G is convex, let's say G1 here is a convex function. So for G1, so we need to have G1 of x hat less than 0. All these points, any point I take inside this will have G1 of x less than 0. And any point on whatever I shaded here, if I take any of those points, for all those points you have G1 less than 0, except for the ones on this boundary, on the circle boundary. Except for the points on the circle boundary, any points I take inside or on this particular line will have Gi less than or equal to 0, G1 less than or equal to 0. And similarly, for all the points for all those same points again, I will have G2 also less than 0. And for all the points on this line, I will have it equal to 0. So these conditions are satisfied, and they have all these points. Whatever point I take inside will actually be a Slater point, right? So this has Slater points. Is this clear? I think there are no questions. We will move on to the next problem then. The Lagrangian dual. Okay, no problem. Yeah, this one we have derived just some time back. So the Lagrangian dual is a quantitative function. Maybe I'll just put that here so it will be easy for reference later. So we derived that this is the Lagrangian dual that is a concave function which we have already derived. You just take just a second. It will be easy later when you refer. So Lagrangian dual is a concave function. So this we already discussed. So moving on to the next problem. So we have this particular optimization problem where you have to minimize this again. This is my f of x. This is my g1 and this is my g2. How many variables are there in the Lagrangian dual of the optimization problem? So if I write the Lagrangian dual, it will be something like d of lambda. There are no equality constraints, so it will be just lambda. That will be infimum. Will be over the x, such that you have to write f of x plus summation over all whatever variables you have, lambda 1 times g1 of x plus lambda 2 times g2 of x. So this is my dual function. So the lambda here will be just a matrix of lambda 1 and lambda 2. Like it's just the number of inequalities that you have. If you have equality constraints, then you will have those also as variables. So here we just have two inequality constraints, so it will have only two variables. Let's take this problem where you have again the same thing. We have f of x as the g of x less than or equal to 0, and then we have defined lambda, okay, lambda greater than or equal to 0 is the Lagrange multiplier. The dual function is denoted by d of lambda. Suppose we are told that d of 5 is 10 and d of 10 is 30. Which of this is valid value for d of h? So when you are given problems like this, all we have to do is use the concave, the logic of concave that we have defined previously. So all we know previously that d of alpha times lambda 1 plus 1 minus alpha times lambda 2. From concavity, we know this will be greater than or equal to alpha times d of lambda 1 plus 1 minus alpha times d of lambda 2. What is the lambda 1, lambda 2 that are given here is the lambda 1 is given as 5, lambda 2 is given as 10. So this is my lambda 1, this is my lambda 2. And now I have to find the alpha somehow from this. So we will use this value for finding alpha. We have alpha times lambda 1 plus 1 minus alpha times lambda 2 equal to 8, which is substitute the values. So this will give me 2 by 5. So once I know the value of alpha, I can directly substitute this. So this is d of 8 should be greater than or equal to alpha is 2 by 5 times d of lambda 1 is 5 plus 1 minus alpha times d of 10. So this will be greater than or equal to 2 by 5 times 10. That is 22. We need to have d of 8 to be greater than or equal to 22. Only one option, so that's fine. So we cannot get the exact value, but we know for sure that d of 8 will be greater than or equal to 22. This is just from using the concavity, this particular relation. So the next one is also something similar. So this also we discussed previously. So when we want to minimize some function f of x such that g of x is less than or equal to 0, and d is the dual function, if x star is optimal solution of the maximum value of d of lambda is less than or equal to f of x. Is this particular statement true? If you write d of lambda, so that will be f of x. Sorry, that will be infimum of f of x plus some positive quantity lambda times g of x. This is some positive quantity and this is some less than or equal to 0 quantity. So the moment you find the optimal value, so this will be f of x star, whatever that x star is the optimal value, plus lambda times g of x star. Again, this is positive and this is less than or equal to 0. This is some finite value. Some finite value times positive times negative. So this will be some negative quantity. So this will be reduced. So this will always be less than or equal to f of x star. So this relation will hold true. So if you try to maximize with respect to lambda, that will always be less than or equal to f of x star. So this again it comes like your weak duality principle. This is my optimal value of the primal problem. This is the optimal value of the dual problem. So the optimal value of dual is less than or equal to the optimal value of primal. Yeah, this one is on the differential dual. Just I put one problem so that the concept will be clear. So we have f star of phi defined in this particular way. This is a differential dual. So consider the function f of x equal to x square, and we need to find the f star of phi by the differential dual function. What is the value of f star of 6? How do we solve this kind of problems? Is again straightforward. So if you have f star of phi as the supremum of with respect to x, you will be varying x to find the maximum of this. So this is just 1D, so I'm just writing y times x minus f of x is x square. So all we are trying to say is f star of I is the maximum of this particular function. So how do you find maximum of this function? If I define this as g of x equal to yx minus x square, I want to maximize this, so I just take dg dx equal to 0. That will give me y minus 2x equal to 0. So x star is y by 2. Once I know x star, I can calculate g of x star is y times x star minus x star square by 2. Sorry, x star square. This will give me y square by 4. So this is the maximum value. Sorry, this is so you can take the double derivative and then you can confirm it. So you have p square g dx square is minus 2. It is negative. So this particular value will be the maximum value. So the maximum value of this is y square by 4. So now you can see how we can convert from primary to dual. Now, okay, from calculation straightforward. Now the question asks you to find f star of 6. That will be 6 square by 4. 36 by 4 is 9. So this is 9. But if you try to plot it in the primal space, the problem looks like this. You're trying to minimize. This is my x square function. This is my x. This is f of x. Let me just write f of x equal to x square. In the dual space, if I convert it, so this is my y, and f star of y is y square by 4. So it will be something like this. But if I want to draw this in the primal space itself, so if you see the line equation is something like this. For any particular value of y, this will be y transpose x minus f of x. So y transpose x minus something, some line will be there. And for that particular line, whatever this intercept is, depending on this intercept value, we'll find the corresponding value here. So if this is y1 and this slope is b1, then this will be y1 and this will be my corresponding b1 value. This is my primal and this is my dual space. I think now it will be clear for whatever question we have asked before. Yeah. The next one is on with respect to the set G that we have constructed before. Here again, we don't have the equality constraints, so I remove the V here. There are only inequality constraints, so there are only two things, U and T. So what is the dimension of this particular set G? It has only two variables. And what is the dimension of U? That will be the number of inequality constraints I have. So I have two inequality constraints, and then I have one objective function. So this will correspond to my T. This will be my U1 and this will be my U2. So K will be equals to both the U's plus the T. If you have equality constraints, then that also will be added. But the dimension of this, the most important thing that I want to show here is this dimension is different from the, this is essentially like combining both the primal and dual spaces. So this U is basically in the domain of constraints. So this will be something corresponding to my dual space. So this U will be the variables in my dual space, and T will be the variables in my primal space. So this K is some kind of, so this G is essentially in a domain where both primal and dual variables are considered. So it will be equal to this. If you have equality and inequality constraints, you have M inequalities and say P equality constraints, then K will be equals to M plus P plus my objective whatever variable that I've used. This will be M plus P plus 1. In this case, M is equals to 2 and P equals to 0. So we have 2 plus 1 equals to 3. This is the last problem I have. So This is again the final theorem that we used about the convex optimization problem. So this particular objective function that we have here is x transpose x is x square. So this is a convex function. And we also know this is a hyperplane equation. So hyperplane is also a convex function. So both are convex. So once both are convex and we are saying A is a full row rank matrix, when it is a full row rank matrix, which means all those constraints when I take the derivative will be linearly independent. So the constraint qualification will also hold. The optimal value of this is, if the primal optimal is P star and the dual optimal is D star, then both of them will be equal. So this is essentially the concept of the strong duality that we discussed. The way we define the duality, whenever you have a convex function with a convex constraint, then that will always be true. Without using the convex constraint, we can only come up till the concept of weak duality. Because if you recall, if you recall, the only thing that we can say from just this without knowing whether function f is convex or not, we don't know whether f is convex or not. If you do not know anything about it, all we can say is the optimal value of dual is less than or equal to the optimal value of primal. That is where we can go up to. Only when we add the extra constraint that this particular function f, g, and h, all of these are convex, then this particular set, whatever we constructed, is also convex. Only in that particular scenario, we came to the conclusion that both of these values were actually equal and the strong duality holds. So in this case, this particular objective function and this particular constraints are convex. So we can come to the conclusion that P star equals to D star. So strong duality holds. Yeah, these are the questions I have for this week. To quickly summarize what we have discussed. So, but before that, you have any questions? I guess there are no questions. So to quickly summarize what we have discussed, so we discussed the concept of constraint qualification, which essentially tells us that the way we define the tangent cone should not have any constraints that are redundant. So how do we remove the redundancy? We gave multiple different qualification theorems. The first one just says that the gradient should be linearly independent. That will ensure that duplicates like this will not arise. So if this then this have a common normal, then the common like the way we defined it, the D is such that the common normal versus this have an obtuse angle. And if two of the constraints have the same common normal, then I can only use one instead of using two. So we can drop one of them. The same constraint is again posed in two different ways. Instead of saying it as equal to 0, we just say that instead of saying it as a linearly independent, we say that G is affine. So the constraints are all will be linear. If they're all linear, then the independence is automatically satisfied. So we don't have to specify it separately. And the other way to say it is instead of depending on the gradients, we know that for a convex function, the gradients will always be the first order approximation is always less than, it will always be greater than, sorry, the first order approximation will always be greater than the actual function value. So we can directly use that information and say that since for the active constraint g of x star is equals to 0 and the gradient is less than 0, the actual we can always find another point such that g of x star is less than 0 if it is convex. And if it is an affine function which is a linear, then the second order derivative will be equal to 0 and this particular thing can actually be equal to 0. All these constraints will again fall back to the same thing, that if you have some way to eliminate the redundant constraints that are present in my original problem in the way I define my feasible set. Next, the concept is of a dual function. So we take the original problem, we formulate the Lagrangian for it, and this Lagrangian will be a linear function in the parameters lambda and theta, and that is what we are calling the dual function when we try to minimize over the function x. The only difference here is we are minimizing it as if we are solving an unconstrained problem. This is very similar to the penalty method that we discussed some time back. So instead of constraining the x to only the feasible domain, that is only this particular set, we are allowing the x to go around all the possible values it can take, and out of all those possible values, lambda and theta can also be anything. So this particular dual function will be a function of lambda and theta, and what we try to find is for every possible value of lambda theta, once we get the d, then we will try to find the maximum value of d by varying lambda and theta. And out of all those maximum values, that particular this particular constraint will always hold, because g is less than 0 and lambda is positive because of the constraint that we kept. F of x star minus this thing will always be less than f of x star. So the optimal value of the dual problem will always be less than or equal to the optimal value of the primal problem. So this is essentially weak duality. And then we thought, okay, under the special conditions, now it's okay, Fitzgerald is not used. Under some special conditions, when you have all these functions to be convex, when all of them are convex, then I can have even more stronger case for the duality, the equivalence between the duality and primal optimal values, and then both of them will actually be equal to each other. Only if this particular thing is satisfied. Or to put it simply, when you have to minimize f of x as the g of x less than equal to 0, all of these are convex. And you have ax minus b equal to 0, and we have full row rank matrix, then there will always be x hat such that this is satisfied. So this is essentially my Slater condition. X hat is my Slater point. So see, if you see this one, this is exactly equal to 0. So these are linear constraints. So this is an affine thing. So for affine, if you recall the Slater condition, for affine things it should be less than or equal to 0. This is equality satisfied. And for convex conditions, we need to have it strictly less than 0, so that is satisfied. So if you can always find some Slater points, then you can always find always the strong duality hold, and the optimal value of primal will be equal to the dual. And then we discuss some of these problems. Yeah. These are the questions I have for this week. So if you have any queries, we can discuss them. Otherwise, I think we can end the session for today. Okay. Thank you for joining.